Let's talk about the binomial theorem. It's the theorem that's going to give us the ability to expand a binomial raised to a power easily and proficiently. Let me remind you of something that I showed in a previous video, and that was how we could expand something like this, 3x plus y to the fourth, because we know something about the pattern when we raise a binomial to a power, and because we can use the binomial coefficients that we find from Pascal's triangle. Let me remind you that this is what Pascal's triangle looks like, and when we're expanding a binomial raised to the fourth power, the coefficients of each of the terms will be found right here in Pascal's triangle in this particular row. So starting with this 1 and the 4 when we're talking about something raised to the fourth power. So if we expand it, let me remind you, these are the coefficients. Let me just put those down. 1, then there'll be a 4, a 6, and a 4, and a 1. And now we don't need to refer to Pascal's triangle anymore, but now we know the pattern of what happens. The first term is used right here and raised to the fourth power. And as we move down the line of the terms, the exponent on this 3x decreases by 1 for each term. So for this term, we would have 3x to the third power. For this term, we would have 3x to the second power. For this term, we would have 3x to the first power. And here we would have 3x to the 0 power, but we don't need to write it. Now, with respect to the y, the exponents on the y are increasing or ascending as we go from left to right. We don't have any y's here, it's y to the 0, but here we would have y to the first, and then y to the second, and then y to the third, and finally y to the fourth. So if we do our arithmetic here, we have 3 to the fourth, which is 81, x to the fourth. Oh, there's a 1 there, 81x to the fourth. Let's see, for our next term, we have 27 because we have 3 cubed times 4. So that's 108 x cubed y. Next, we have 3 squared, that's 9. Times 6, 54, x squared, y squared. Next, we have 3 to the first power, or just 3 times 4, which is 12, xy cubed. And our last term is just y to the fourth. So it wasn't so challenging to raise 3 plus y to the fourth power, as long as you have practiced that pattern. But what if the problem looks more like this? Suppose the question were to find the first 4 terms in the expansion of x plus y to the 23rd. Well, we could do it the same way. The problem is right here on our Pascal's triangle, it doesn't go low enough. We know it would be way down here and would start with a 1 and a 23. In fact, we could write the first few terms, or first couple terms. We know x plus 4y to the 23rd would need to start with a 1. And then we'd have x to the 23rd with no 4y at all. Our next term would be 23, x to the 22nd, and now 4y to the first power. And here's where the problem happens. We're not low enough on Pascal's triangle, and I don't want to have to keep going down here to get to the line that would have those coefficients. So we want to find another way to find those binomial coefficients. But let me point out before we move to that we do know what the rest of it should look like. It's something times x to the 22nd, 4y to the second, and the fourth term would be let's see, x to the 23rd, x to the 22nd, this should be x to the 21st, and then x to the 20th, 4y to the 3rd. The only thing we're missing are these two coefficients. So that's where our task lies now. How do we find those coefficients? And we'll come back to this problem. Now I'm going to talk about something else that for a moment will feel unrelated. We're going to talk about factorials. And let me remind you of what that is, or tell you what it is in case you haven't seen it before. We define n factorial to be n times n minus 1 times n minus 2 times, and keep going until you get down to 1. And n can be any positive integer. So if we were looking to find 6 factorial, it would be 6 times 5 times 4 times 3 times 2 times 1. And if you multiply those together, you'll find that it is 720. Or 3 factorial is simply 3 times 2 times 1, which equals 6. 1 factorial, not super exciting, is just 1. But what if we have 11 factorial? Certainly we could write it out 11 times 10 times 9 and keep going until we get times 3 times 2 times 1. And we could grab our calculator. But I really wouldn't even want to punch in 11 times 10 times 9 times 8 all the way down to 1. And fortunately, scientific calculators are already programmed in with their factorial button. Let me bring you in on this particular calculator. And I'm going to show you where it exists. So on your calculator, you'd need to find it. Sometimes the factorial button is visible and you can see it over one of the buttons or on one of the buttons. On this one, and this is pretty common, the factorial is under this PRB for probability button. So if I wanted 11 factorial, I'd push 11, the probability button, and notice the factorial is over there. So I'm going to scroll over to that factorial and press enter on it. So I hope you can see on my screen it shows 11 factorial, and I press enter. And we have that very large number. It looks like 39,916,800. And so you can see that factorials get very large very quickly, and that was just 11 factorial. Now we're going to leave that alone for just a minute. We'll come back to that idea of factorial. I want to show you something else, and then we're going to tie these pieces together. We have a notation that looks like this mathematically. That's an n and an r inside these parentheses. And often it's read n choose r, or n taken r at a time. And you'll hear me just say n choose r, and I'll talk about what that means in a minute. It's defined to be n factorial divided by r factorial times n minus r factorial. Now let's try a problem. Suppose we were calculating 5 choose 2. We can do that. It is 5 factorial divided by 2 factorial times, now right here is the difference between those factorial. So 5 minus 2 is 3, so it's 3 factorial. So I'm going to do this calculation. Now the numbers are reasonable enough. I don't need to grab my calculator. I know that's 5 times 4 times 3 times 2 times 1 over 2 times 1 times 3 times 2 times 1. So let's do our canceling. 3 times 2 times 1 cancel. And look at, I have a 2 here that I'm going to cancel with that 4. So I'm only left with 5 times 2 in the numerator and a 1 in the denominator. So I get 10. Before we do some more calculation, let me just talk about this a little bit. I read this as 5 choose 2. what this represents, let me pull this down. I didn't have it lifted once I put the calculator away. Sorry about that. So what this represents is the number of possible combinations if you have 5 items and you select 2. So just think about 5 items thrown in a bag. You reach in, randomly grab a pair. How many different possible combinations are there? And let me just show you that it is 10. Let's let the 5 items just be represented by A, B, C, D, and E. So all 5 of those are thrown in a bag. Now you could grab these first 2 items, A and B, or A and C, or A and D, or A and E. And those are the only combinations with A. And we're assuming that A and B is the same combination as B and A. In fact, mathematically, we do say that they're the same combination. There's no particular order. You're just looking at the 2 items, and whether you have A and B or B and A, it doesn't really matter. It's the same combination. Now let's look at the combinations possible with B. We already have the AB, but we could have BC or BD or BE. Now the combinations with C, we already have C and A and C and B, but we don't have C and D or C and E. And D, we already have some of the combinations, but we don't have D and E. And we have all the possible combinations if you were to take 2 out of this list of 5. And notice we have 4, 7, 8, 9, 10. So this gives you the number of possible combinations if you have 5 things and you take them 2 at a time. So if we were to calculate 7 choose 1, let's do the calculations. It is 7 factorial over 1 factorial times 7 minus 1, which is 6 factorial. Not hard to write this one out. 7 times 6 times 5 times 4 times 3 times 2 times 1 over 1 times 6 times 5 times 4 times 3 times 2 times 1. And these cancel. And we get 7. And if you think about it, I hope this makes sense. Because if we have 7 items and we just choose 1, there are only 7 possible things that could happen. Any one of those 7 items could have been chosen. Let me mention this. Suppose you had this. 7 choose 7. What would you expect the result to be? Well, if you have 7 items and you reach in and you choose all 7, there is only one way that that could happen. You grab them all. We expect the answer to be 1. But let's look at what that means. That means that 7 factorial divided by 7 factorial times 0 factorial must equal 1. Notice the 7 factorials cancel. And we have 1 over 0 factorial equals 1. And that must mean that 0 factorial equals 1, which does seem to bug people a little bit, but we define it to be 1 because in the places where you see factorials used, 0 factorial always makes sense, as it does here, even though it bugs people. And let me mention, it's programmed into your calculator that way. If you punched in 0 factorial, let me turn the calculator on, and we punched in 0 factorial, you'll notice that it does come up as 1. But sometimes even with bigger numbers, we don't need to use our calculator. Suppose we had this combination, 100 choose 98? Well, the formula says that's 100 factorial divided by 98 factorial times 2 factorial. Remember, this is n factorial. That's r factorial. That was n and the r. And this is n minus r factorial. Let me bring this page up. I think maybe you didn't see that very long since I had the camera a little bit too close. But here's the formula that we're using. But we can do this by hand. Now, I don't want to write 100 times 99 times 98 all the way down to 1, but I could write 100 times 99 times, now the rest is 98 times 97 times 96 times 95, all the way down to 1. That's just 98 factorial. And so I can simplify it this way and cancel my 98 factorial. And further, I can reduce here. I have this 2 and this 100. So I would just have 50 times 99. And if you do that arithmetic, 50 times 99 isn't too bad. We have 4,950. So if you have 100 items and you're choosing 98, there are 4,950 different possible combinations. Now, if you're thinking, we've gone a long way from expanding binomials, well, let me tie this back to our binomials. And to do that, we're going to look at these combinations. And let's start with a clean piece of paper. That doesn't look clean enough to me. Let's do this. Let's look at 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, and I'm determined not to let you see everything this time. 4 choose 3, and 4 choose 4. And let's do our calculations. This one, really, let's think about it again. It's you take you have 4 items, you take no items out of that. How many different ways can you do that? Well, it's philosophical almost. There's only one way. You don't choose any. But mathematically, it is 4 factorial over 0 factorial times 4 factorial. Our 4 factorials cancel, and we just have 1. Keeping in mind that 0 factorial is 1, we have 1 divided by 1, or just 1. Our next one, 4 factorial over 1 factorial times 3 factorial. So we have 4 times 3 times 2 times 1 over 1 times 3 times 2 times 1. We do our canceling. And we have 4 over 1, or just 4. Let's get to the next one. 4 factorial over 2 factorial times 4 minus 2 factorial, which is another 2 factorial. So we have 4 times 3 times 2 times 1 over 2 times 1 times 2 times 1. This 2 times 1 cancels. We have a 2 and a 4. Let's reduce those. So in the numerator, we have a 2 times 3, and in the denominator, we have a 1, and that's a 6. Our next one, we have 4 factorial over 3 factorial times 1 factorial, and I'm about to write it out, and then I realize, hey, those two are completely equivalent, so those numbers would be the same. So this will also be 4. And for this last one, I have 4 factorial over 4 factorial 0 factorial, which is again equivalent to this one, and again is just 1. Keeping in mind, this is how many different possible combinations there are. When you have 4 items and you choose 4, there's only one way to do it. You scoop up all of them. So now I want you to see these numbers. We have 1, 4, 6, 4, 1. And I hope that looks familiar. look back here at our Pascal's triangle. Right here in this row, these numbers that we found are these coefficients. In fact, these numbers that came from our combinations are actually the numbers on Pascal's triangle. They are the binomial coefficients when you expand a binomial. So let's write up what the binomial theorem actually says, and then we'll use it. The binomial theorem says that we can expand a binomial this way. A plus b to the nth is found by taking the a and decreasing the powers until you get down to no a's. And the b's start with b to the 0, b to the first, b to the second, keep going until you get b to the n. And look at the coefficients. They are n choose 0, n choose 1, n choose 2. Keep going until you get to n choose n. So that's how we can find the coefficients when we're expanding a binomial. So let me take you back to the problem that we did a few minutes ago, or we started a few minutes ago. It looked like this. We just didn't know what these coefficients were. And let me just mention that when we are raising to the 23rd power, the binomial coefficients are 23, choose 0, 23, choose 1, 23, choose 2, 23, choose 4. So these are the numbers that would be our coefficients. So this one right here is 23, choose 2. This was 23, choose 0, 23, choose 1, 23, choose 2. And I don't know why I wrote 23, choose 4. It was 23, choose 3. They increment by 1. 23, choose 3. So our task is to find these. So we have x to the 23rd plus 23 times 4. We can do that. 23 times 4 is 92. 92, x to the 22nd, y to the 1st, plus, now we have 23, choose 2. We could use our factorial button. Remember 23, choose 2 is equal to 23 factorial over 2 factorial times 23 minus 2 factorial, which is 21 factorial. We absolutely could do that. We could do it by hand, or we could use our calculator. But I want to show you one more thing on your calculator. These combinations are so common that most scientific calculators already have those programmed in as well. The notation that you often see in the calculator is this: a combination of 23 items taken 2 at a time. You have a 23 and a C and a 2. So that's what you would look for on your calculator. I will tell you, they come up right near the same place the factorial button came up. So let's do it. We're going to do 23. I'm going to push the probability button. And can you see right here? I'm going to come in. I'll try to remember to bring the camera back out this time. Here it is, this NCR button. We're going to select that one. And then we put in our 2 and press enter. And we can see that we get 253. So this is 253 times x to the 21st times 16y squared. And this one is 23, choose 3. So let's use our calculator again. I'm just going to edit it and change the 2 to a 3 and press enter. and I get 1,771 x to the 20th times 64, we have 4 cubed, 64y cubed. And let's write that a little bit neater. So we have x plus 4y to the 23rd equals x to the 23rd plus 92x to the 22nd y to the 1st, plus we have some arithmetic to do there. I'm going to grab my calculator. 253 times 16 is 4,048 x to the 21st y squared plus 1,771 times 64 is 113,344 x to the 20th y to the 3rd. And we have our expansion of the first 4 terms of the expansion of this particular binomial. Would be a much bigger task if we needed to find all the terms. And in fact, I have an equals. That technically is not an equals there. These are the first 4 terms in the expansion of that binomial. Do keep in mind that with binomial to the 23rd power, you would have 24 terms in the expansion, and we just have the first 4. Let's do another problem. Let's let it be this one. Find the 3rd term in the expansion of x minus 2y to the 30th. So we know for the first term, the binomial coefficient would be 30 choose 0. Then we'd have 30 choose 1. Then we'd have 30 choose 2. So this coefficient is 30 choose 2 for the binomial coefficient for the 3rd term. Remember, the first one is 30 choose 0, and the second one is 30 choose 1. So we're at 30 choose 2. Now our x's, we start with x to the 30th, then we'd have x to the 29th. So when we get to this term, we're at x to the 28th. And we have negative 2y that we're raising to a power right here. We would start with negative 2y to the 0, negative 2y to the 1st, negative 2y to the 2nd, and these 2 exponents always add up to our exponent here. So now we can expand this. 30 choose 2. I'm again going to use my calculator. If you prefer just to do it by hand, let me remind you, it is 30 factorial divided by 2 factorial times 28 factorial, which is actually pretty reasonable even to do by hand. In fact, shoot, I want to. That's 30 times 29 times 28 down to 1, so that's 28 factorial over 2 times 1, that's our 2 factorial, and our 28 factorial. So our 28 factorials cancel. Our 2 and our 30 reduce. So we really have it just boiled down to 15 times 29. So that is 435 for this number. X to the 28th times 4y squared. And then we multiply 435 by 4. And we have 1740 x to the 28th, y to the 2nd. So this is the 3rd term in the expansion of that binomial. Let's do one more. Let's make it this one. Find the 15th term in the expansion of this binomial. Now, because we're raising it to the 16th power, there are 17 terms. So we don't want the last term. We don't want, which by the way would be 16 choose 16. We don't want the one prior to that. That would be 16 choose 15. We want the one right before that, the 15th term, which would be 16. I'm going to move it over here. 16 choose 14. Now, starting on the right, this is y to the 16th, y to the 15th, and now we'd be to the y to the 14th. These two exponents will add up to 16. That means I have x to the third raised to the, must be the second power. Again, we could do this by hand, but let me point out one more time, and this time I will do it on the calculator so that you know that that's totally fine. 16 choose 14, so you punch in your 16, find your combination button, probably near your probability, and there it is. Don't use your NPR, that's something else. NCR, that C is for combination, and then we need 14. So this 16 choose 14 is just 120. So I would have 120 x to the 6th, y to the 14th, and we have the 15th term in the expansion of this binomial.